Welcome everyone. In this video we are going to talk about how to take the natural logarithm of a negative number. For example, if I were to ask you what is ln of negative 3, you would say this is out of range because ln is defined for numbers that are greater than or equal to 0. Not greater than or equal to, excuse me, that are greater than 0. Even if this is ln of 0, well, that is undefined as well. Okay, so you might say that to me and you would be right. That's completely fine. But if we are considering the complex plane as well, because let's think about this. If we have complex number as well, if I say what is ln of I, how do you handle this? And if you are able to handle this, it turns out that you also have an answer for this. Okay? If you bring complex numbers into play, then you can take the natural logarithm of a negative number and the result is going to be a complex number. It's going to have a non-zero imaginary part. Okay? And in this video I will show how that is doable. So let's try that. And you still can take ln of 0 though. Yeah. I'm thinking about it. Yes, even the method that I'm about to show you won't work for 0 if I'm correct, and if I'm wrong, please correct me in the comment section. Okay, so how do we start? Well, if we consider some complex number z, and if we take its natural logarithm, we could write it like this, ln z. But since we have been using ln, this function for real positive numbers, let's use a different function. Maybe you can think of it as a more general logarithm function, capital ln z, okay? And this is, let's say, w. This is the same, this acts as the good old ln that we are used to. So if you raise it to the power of e, if you raise e to the both sides, then you have that z is equal to e to the power of w, okay? And here, I want to demonstrate one property that we know very well from the natural logarithm that we are used to. If we multiply z1 and z2, two complex numbers, can be expressed like this, and by the rules of exponents, we know this. If we take the ln on both sides, notice the capital L. Well, this is going to be, by the definition, it's going to give back the power of e. So that's what we have. And you can also see that this is equal to this part, right? So you can separate one ln. The ln of a product can be written as the sum of two ln's. We knew this for real positive numbers. We also know it for complex numbers now. Okay? Now, if I were to now express z like this, it's going to be r e to the power of I theta. This is a way to express complex numbers. The way it works is a geometric way. So this is the real number line, this is the imaginary one. If the point is here, if the number is here, r is the radius and theta is the counterclockwise angle from the real axis, okay? And you can see that if we were to have the same theta, and if we add 2 pi to it, that is, if we rotate one full circle, we are back where we started. So you can add 2 pi to it, but in fact, you don't need to rotate once or twice. You can rotate as many times as you want, as long as it's an integer. You can even rotate in the clockwise direction rather than the counterclockwise. So we put a n here. N is an integer, okay? And so this is the most general way to, this is a general way to express a complex number, okay? And depending on the value of theta, the number can be real. If theta is 0, well, then the number sits on the real axis, so it's a real number. Or if theta is pi over 2, it's an imaginary number, completely imaginary. Cool. Now, if we were to take the ln of this complex number, and this is the new ln function that we're defining, it's going to be ln of this product, and we just saw that we can treat products as we used to for the natural logarithm function that we already know. So that's the value that you have. And this can be written as the good old ln r with a lowercase l, because r is a real number and it's in fact a positive number. We can not consider it as the radius. It can be negative, but we really don't prefer to write it negative. In the polar form, the convention is to choose it as a positive number. And even if it is negative, you can always toss it into theta and you make r a positive real number, okay? So we have that, and the other part is just by the definition going to be the power of e. So ln r plus I theta plus 2 pi n. As you can see, this is multi-valued because n can be any number as long as it is an integer. If I want to get rid of this multi-valued situation, I can define ln z just like the way we wrote it in the past. And this is going to be called the principal value of capital ln z. The thing is, it's going to be, so this is the principal value of the general one, let's say. And for this, theta is going to be less than or equal to pi and greater than negative pi. I made this exclusive because, like, by doing this, we are already covering the whole range. What I mean is, pi covers this part and this point as well, and negative pi covers this part. We don't need to cover this point again, okay? So this is including all the range, and we choose n to be 0. Cool. So for example, if we had pi over 2 as the argument of the complex number, the angle is called the argument, we wouldn't write it as 5 pi over 2. They point to the same picture, same point geometrically, but to deal with smaller numbers, we just choose n to be 0, okay? This is a convention. And so, returning to our question, what is ln of negative 3? We first want to compute the capital N of negative 3. This is going to be, we need to express 3 in terms of this. And this is equal to r cosine of theta plus I sine of theta. If you don't know where this comes from, it seems irrelevant, it seems unexpected, and it is unexpected maybe. But lucky for you guys, I have a video where I prove this, so you can access that video from the cards right now and also from the descriptions part. This is sometimes called the Euler identity. I think it is super duper important. It is incredibly important. Please make sure you understand how this and this are equal. And if you look at this, we said that r is a real positive number. It's going to be 3. And if we choose theta to be pi, this is 0 and this is negative 1. So we get back negative 3. Which means that negative 3 is just 3 e to the power of I pi. And this is going to be ln of 3 plus ln of this, right? And we can make this a smaller ln of plus I pi. And, well, actually, so the thing is, hold on. I didn't include something that I should. So, of course, here for the argument, you could put 2 pi n, right? Because just we discussed, we are back at where we started. There is 2 pi n here. Plus 2 pi n. Okay. This is the, let's say, general one, ln. If we are considering the principal value, which we are considering, it is going to be ln 3 plus, and we choose n to be 0, and then I pi. As you can see, this is a complex number with a non-zero imaginary part. And similarly, you could discuss ln I. You would need to express I in terms of, so let's see, what is I? It's going to be r cos pi over 2, I think, yeah, pi over 2. So I is just equal to e to the power of I pi over 2, and if you now take its, well, we can also add this one, I guess. So if I take the ln now, let's just give us more room. ln I is going to be then I pi over 2 plus 2 pi n. So if we consider the principal value, it's going to be I pi over 2. It is also an imaginary number, as you can see. And why do I think we can't take the natural logarithm of 0 with this method? Because if you were to consider 0, like ln of 0, how do you express it in terms of this? R should be 0, and, well, that doesn't give us any place to go. Theta could be anything in that part, and you get like something weird like this, I guess. ln of 0 plus e I pi, so like this. Okay. And we still don't know how to handle this, so we can't discuss this. We can't do this, as far as I can tell. But as I said, if I'm wrong, please let me know, and I will learn from that. Anyways, this is it for this video. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.